This tutorial will describe how to do basic molecular mechanics calculations. Let's first create a molecule. We'll go and create a small peptide. We'll use an alpha helix. We'll put a blocking ACE group on one end, and then four gly, and then a me on the other end, a blocking group to put on the ends. This is our small peptide. If we wanted to look at this, we have some hydrogen bonds there. One hydrogen bond, I guess. Now, if we want to do molecular mechanics, we go and first of all choose a methodology. We can choose MM+ amber, charm, OPLS. We're going to use amber. Let's then choose some of the options. We can use a constant dielectric appropriate to gas phase or when we have real water molecules, or a distant dependent dielectric which simulates having some dielectric water medium or something of the sort. We can scale the 1:4 interactions. This is the standard amber procedure. We have the possibility of adding long-range cutoffs to the potential. We're not going to do that here. So basically the options are pretty straightforward. The normal ones, we just select them. The components, we have the option of including or not including different terms in the force field and the potential. There's the bonded term, the angle term, torsion term, the non-bonded van der Waals type interactions, the electrostatic charge and dipole interactions, and potentially a hydrogen bonded term. Depending on the force field, some have hydrogen bonded potentials and some do not. Anyways, we basically want to use all the components in most situations unless we're doing a specific test. So that just chooses the amber force field. Next, what we want to do is select a parameter set. With amber, there are these various parameter sets for amber. These first two are an older version of amber. This is a version of sugar parameters for polysaccharides. These last three are newer parameter sets, amber 99 being the latest one. If you select one of the first three parameter sets, you actually get the old force field, whereas if you select one of these three parameter sets, you get the newer force field, the Cornell et al. Force field, the newest version of amber with one of these parameter sets. It uses which parameter set you choose to decide on which force field to pick of the two amber force fields. So we'll just use the newer one, and then it's more or less go ahead and do the kind of calculation you want. We generally have lots of different options or similar options for whatever methodology or engine we choose, but let's just go ahead and optimize this structure. This is shouldn't take too long, but I'm not quite sure how long it will take. I haven't tried this particular calculation before. I guess it's going to go fairly quickly. So we're now converge. That's the structure. We might recompute the hydrogen bonds because the hydrogen bonds might have changed in the optimization. In actual fact, we now have two hydrogen bonds where before we had one. Those hydrogen bonds are not updated during the optimization. You actually have to explicitly ask to see the hydrogen bonds or recompute the hydrogen bonds if you want to see hydrogen bonds. Anyway, that's the basic computation of the molecular mechanics result.